Welcome to episode 9 of the Euler Project, a series in which we use Clojure to solve the problems on the online Euler Project, and then we take them where no one has gone before. Problem 9 is a simple little ditty that asks us to find a particular Pythagorean triplet. Each number in the triplet must be an integer, and they all have to add up to 1,000. So this shouldn't be too difficult, right? I mean, all we have to do is find three numbers, a, b, and c, that add up to 1,000, and where a squared plus b squared equals c squared, right? I mean, it's a Pythagorean triplet. Can't be that hard to find. This sounds like a simple triple nested loop between the numbers from 1 to 1,000, right? That's probably overkill, but let's give it a try. So, I mean, this is not rocket science, right? I've got a triply nested loop here. We're going to loop with A, B, and C going from 1 to 1,001. Why did I pick 1,001? Well, I don't know what the maximum of A or B or C is. I know it's got to be something less than 1,000 because they all add up to 1,000. But who knows? I mean, either of them could be 999. So, okay, let's just run them all to 1,000. And then we constrain the loop here with this when clause saying, yep, okay, they all three have to add up to 1,000, and c squared has to equal a squared plus b squared. So, typical kind of Pythagorean triplet. And yes, I'm going to execute it with a test because why not? I could do it in the REPL, but I've got this testing framework, might as well do it here. And I run this, and of course the test fails because I'm comparing to a nil, but the result is shown here. And notice that I get two results. I get 200, 375, 425, and 375, 200, 425, which is the same triplet, just with A and B swapped. So that's fine, lovely. It all worked, and it took about 20 seconds to run. Yeah, okay. Maybe not the best, but okay. Yeah, okay, so that was a billion loops. Did I need to run a billion loops? No, I didn't really need to run a billion loops. I mean, I've got two equations and one inequality in three unknowns, right? So I ought to be able to do something better than a billion loops. So what if, instead of looping through the integers 1 to 1,000, we loop through the squares of 1 to 1,000 and we do a double loop? And the double loop will add two of those squares together and see if the sum is another one of those squares. Okay, so we're going to find all the triplets that add up to 1,000. That's what we're going to do. And we begin that here by finding all the triplets. So all the triplets whose numbers are less than 1,000 or less than or equal to 1,000. And this will return a list of all those triplets. And then we filter that list with this predicate. And the predicate is simply that the sum of the three numbers in the triplet add up to n. And that should give us our answer, which you see down here it does, right? 200 and 375 and 425. That was the answer we got. Notice that it took a third of a second, so that's pretty good. But of course, how did we find all the triplets up to n? Well, that's up here, and it's pretty straightforward. First thing we do is we create a list of numbers from 1 up to n. And remember that range doesn't include the last one, so you have to increment, right? So, okay, these are all the numbers from 1 to 1,000. And then we create the list of the squares of all those numbers. So we just map the squaring function, that's the squaring function, over the list of integers, and we get the set of the squares. I turned it into a set because I want to use this contains function here. So the triplets are, and here's our for loop, and we're only going to loop a doubly nested loop. We're going to loop A and B over the squares. And when the sum of those two is in the square list, then we know we've got a triplet, right? Because A plus B is C, and A and B are both squared, and C is squared, and so that's A squared plus B squared equals C squared. And so we know we've got a triplet, but we need to figure out what the triplet is, so we have to take the square roots of A and B and of the sum, and turn them into integers just to be polite. And then we filter out all of the nulls, all of the nils, because the for loop will create an answer for everything, even though it doesn't have the when in it. And so the filter will take out all the nils. And then finally, we filter out any that are in reverse order. So we make sure that A is less than B is less than C. And that's how you get all the triplets. And that's nice and fast, and it gets the right answer. Does that work? Well, it looks like it does. I mean, 200 squared is 40,000, and 375 squared is 146.25. You add those two up together, you get 186.25, and that's what 425 squared is. So that much works. And then 200 plus 375 plus 425, well, that equals 1,000. So yeah, I guess that triplet works. Yeah, so I guess we're done, right? I mean, we found the Pythagorean triplet whose elements add up to 1,000, and those elements are 200 and 375 and 425. So yeah, I guess we should just pack it up and go home. On the other hand, we just made a bunch of pretty nifty tools that would allow us to explore the whole realm of Pythagorean triplets. Like, let's just find all the triplets whose numbers are 100 or less. So yeah, I mean, all I do is call that find triplets function up to 100 and, compare it to nil in my test, and my test will fail, but it'll give me the answer, and here's the answer, and it's an awful lot of triplets, isn't it? And let's see, we ought to be able to find like 3, 4, 5 in here. Shouldn't, I see something like 33, 44, 55. Well, that's really the same as a 3, 4, 5 triangle, isn't it? Oh, look, 6, 8, 10. That's the same as a 3, 4, 5 triangle. Okay, yeah. I probably don't want all the multiples, do I? So let's get rid of all the multiple triplets and find all the actual unique triplets. So how do you find the unique triplets? Well, I guess what you do is you look for triplets that are mutually prime, right? You make sure that the numbers in the triplet are mutually prime. Didn't we solve a problem like that in a previous episode? I think it was episode 5, wasn't it? Yeah, it was. It was episode 5. And in episode 5, we wrote this greatest common denominator function here. And I've extended a little bit so that we can take the greatest common denominator of n elements just by reducing the list over a GCD. So that works just fine. And so how do we find unique triplets? Well, we find the triplets up to n, and then we filter for the GCD of 1. So they are mutually prime if the GCD is 1. And then we sort those by the first number so that we kind of get them in a reasonable order. And here's the result down here. It's pretty cool, right? 3, 4, 5 is the first one, which makes perfect sense because there's no Pythagorean triplet, at least no integer Pythagorean triplet that begins with a number less than 3. And 5, 12, 13. Okay, high school geometry, you probably remember that. And I don't know if you remember 7, 24, 25, and 8, 15, 17, but here they are. They're all Pythagorean triplets. And isn't it interesting that there are so many that have a difference of 1 in the B and C category there? Isn't that interesting? Well, anyway, there are still quite a few triplets, but not nearly as many as before. Well, that's kind of interesting. Now, each one of these triplets represents a right triangle. And these are rational right triangles because they're all made of integers. I just coined that term, rational right triangle. I don't know if other people have used that term before, but I just coined it. That's my term now. These are rational right triangles. Wonder what they look like. So here's a 3, 4, 5 triangle. Pretty easy to draw. I just kind of used the eraser to measure the sides here. It wasn't very hard. But then this one, this 5, 12, 13, that was a little harder because I didn't have enough eraser marks to get up to the top, and so I cut the eraser in half. And this is kind of drawn to half scale. And well, you notice it's a slightly different angle than the 3, 4, 5 triangle. And then here is the 7, 24, 25 triangle, and I use the same half scale here. Goes up 24 half eraser units and 7 half eraser units here. And that's interesting, pretty narrow triangle. Now, I mean, that's interesting and all, but wouldn't it be nice if we could see them all at the same scale? And what is it that we mean by the same scale, right? Like, wouldn't it be nice if we could overlay all these triangles on each other? You know, like maybe this left edge here, maybe we made that the same size in all the triangles and then just drew them on top of each other. So remember way back in episode 2, we came up with that turtle graphic system where we could draw things, and we've used it several times since. So what I've done here is I've written a cute little thing that draws the triangles from our function, find unique triplets, up to 1,000. So we're going to draw a lot of them here. And well, I mean, here I can show you the code, but maybe you don't want to see the code. I'm not sure. Here's how you draw triangles. This is a whole bunch of triangles, which takes a list of triplets. And I'm not going to go through this with you, just to say that it goes through all the triplets and draws them with the triangle function. And it also draws a scale, and it draws there's the scale, and it draws the axes, and then when it actually draws the triangle, it scales the triangle properly so that they're all roughly the same size, more or less, right? So, well, here, let's just run it, and you can kind of see how it goes. Yeah, so that was the scale, and you can see it's divided into tens. And now, these are all of the Pythagorean triplets from 3, 4, 5, all the way up to numbers that are close to 1,000. And it's kind of surprising, isn't it? That the A side is scaled so that it's always at full scale. And then the B side is the one that changes. Or maybe it's the B side that's scaled and the A side that's changed. I'm not quite sure which. And the real calculation here is the calculation of the angle up there at the apex. That's the only thing that really changes. And you can see that's kind of interesting, isn't it? I mean, there's an interesting pattern showing up. First of all, there seems to be well, I don't know if it's a hard limit, but there seems to be a limit at the narrow side. We'll talk about that in a little while. And of course, there's definitely a limit on the far right side, which looks like it's when A and B are equal. Of course, that would not be a rational triangle, would it? Because the hypotenuse there is the square root of 2. And then there's these interesting lines with gaps around them. So, okay, this is interesting. We'll let it finish, and I don't know how many triplets it's drawing. It's quite a few. Now that's a fascinating pattern, isn't it? We should think about that. First of all, don't you think this pattern looks a little bit like the rings of Saturn? I mean, maybe you've got to squint. So now let's look at this pattern. There's two obvious things about it. It looks like there's an asymptote on the left and an asymptote on the right. Now the asymptote on the right's not too hard to figure out, right? That's where A equals B. And that's an isosceles right triangle. The hypotenuse is the square root of 2, so it's an irrational right triangle, which cannot be one of our triplets. So that makes perfect sense. The asymptote, or the apparent asymptote on the left, is more interesting, because that's where B equals C. Is that an asymptote? On the left, we see these really narrow triangles, right? And they occur because B and C are very close to each other. But B and C are always separated by the base A, right? So I wonder how small that base A can get. As you can see from this time-lapse movie going on behind me, those triangles creep ever closer to the left, but they never seem to get any closer than about 0.045. Could there be a hard limit there somewhere? Now remember that these are rational triangles, right? They're all made out of integers. So these narrow triangles on the left, they must be of the form A, B, B plus 1, right? B and C are as close together as they can get, but they can't be equal, right? So since they have to be integers, it's going to be A, B, and B plus 1. Now, I've got a little bit of math down here that shows how that works out. And up here, I've shown you some of the triplets that we've discovered that are of this form. I call them twin triplets. So there's a bunch of them in there. There's bound to be. So, okay, here's the math. And I'll let you work out the math if you want to. It's just high school algebra, nothing big deal. But in the end, we see that A is going to be equal to the square root of 2B plus 1. Now, what does that mean? Well, it means that as B gets larger, A gets larger too, but by a much smaller amount. Right? The rate of growth is much smaller. That radical sign means that A grows quadratically slower than B does. And because of that, I conclude that there is no lower limit on A. That angle at the apex of the triangle can get as small as possible without ever quite getting to 0. The asymptote is 0. The asymptote is when B equals C. But of course, B can never equal C because C is equal to B plus 1 in every case. So I think that those triangles can get narrower and narrower and narrower without limit, asymptotically approaching a 0 angle at the apex. Now, what are those gaps in the pattern? Now watch that first big gap. It was drawn by the 3, 4, 5 triangle. That's the line down the middle of it. Now watch, the other triangles will get closer and closer and closer to it. I guess that if we let this run far enough, that gap would close. Well, it would asymptotically close. But why are those gaps there at all? 3, 4, 5 is a triplet of small numbers. There aren't a lot of triplets of small numbers. They're fairly rare. And that particular triplet has an AB ratio of 3/4. Now, there aren't a lot of triplets that have an AB ratio of 3/4. And in fact, the numbers have to start getting fairly large before they can approach another AB ratio of 3/4. So that's why there's that gap there. As the numbers get larger and larger, that gap will narrow and narrow. But 3/4 is kind of like a repulsive area because it's hard to get large numbers that have a ratio of 3/4. And the same is true of the other triplets that have small numbers in them, like 5, 12, 13, and 7, 24, 25. Although in that case, it's to a lesser extent. Those ratios are a little bit easier to approach. Who knew that Pythagorean triplets could be so interesting? Who knew that they looked like the rings of Saturn? Anyway, that's the episode. I hope you enjoyed it. I hope you had fun. I hope you learned a thing or two. But you're not going to want to miss the next exciting episode of the Euler Project, episode 10, the summation of primes.